Okay, let's talk about computer systems. Computer systems consist of hardware and system software that work together to run application programs. The software is a collection of instructions and data that tell the hardware what to do. The operating system is a giant system software that manages computer hardware, software resources, and provides the common services for computer programs. On top of OS, the applications run to perform their own tasks. Web browsers, office applications, multimedia applications are among the applications that we use every day. Hardware is what makes the physical system, that is, a physical device that we can touch. The processors like CPU and GPU, input and output devices such as a keyboard, mouse, and monitor, and buses and memory are among common and important hardware components. A simplified system stack is shown on the right side. At the bottom, we have hardware. Next up, we have a OS that controls and manages the hardware. And on top, we have applications that we run as we need. Let's talk briefly about C programming language. The C language is originally developed at Bell Lab in 1972. It's one of the oldest and still most popular high-level programming languages. What makes it special is that the C is a language of choice for system programming, such as operating system and device drivers. It's because they are fast, efficient, and give you a direct access of memory, as it provides programming constructs that map efficiently to physical machine instructions. Unlike most of other programming languages, C supports the use of pointers, a type of reference that records the address of an object or function. You might hear about C++. So C++ programming language is an extension of C with object-oriented programming paradigm. Therefore, C++ is a big brother and superset of C and can understand the C without any problem. It's time to talk about compilation. Because hardware cannot understand high-level programs, we have to first compile to generate machine code. Compilation is a fairly complex and intelligent task, whose goal is to generate the machine code that runs efficiently on hardware. Compilers apply hundreds of optimizations during its code transformation process. Compilation typically consists of 4 substages. First, the source program is preprocessed by a tool called preprocessor. For C program, the preprocessor simply copies and pastes the contents of header file included in the source program. This is a fairly straightforward and copy and paste task. The modified source program then is fed into the second stage called the compile. A tool compiler transforms the modified source program in high-level language into assembly program in a completely different low-level language. This task is a core part of compilation, where most significant and intelligent changes are made. Note that assembly program is still in text format, meaning if you open the file using a text editor, you will be able to read the assembly program. The third step is assembling. A tool that does assembling is called assembler. The assembler encodes each assembly statement into a binary machine command according to the target processor microformatting rules. These one-on-one mapping rules can be found in the processor architecture document. The output of assembling is no longer in a text format if you open it using a text editor. Unreadable garbage like weird symbols will be shown on the screen. The fourth and the last step is linking. A tool called linker merges multiple binary files also known as object files, into a final single executable binary file, which is ready for execution by hardware. The diagram visualizes the compilation process as well as conventional tools and names that GCC compiler uses. Input source program hello.c is pre-processed into hello.i by a tool named CPP. Hello.i, the modified source program, then is compiled to hello.s by a tool named CC1. The assembly program hello.s is assembled to the hello.o binary file by a tool named AS. Finally, the hello.o relocatable object binary file is linked with the other binary object files and become the final executable binary file named hello. Note that the hello.c, hello.i, and hello.s files are plain text files, while hello.o and hello files are binary files. Assembly language is a low-level programming language which is a human-readable textual representation of machine code. Each statement in assembly program corresponds to a single machine instruction. Each assembly language is specific to a particular processor architecture called the instruction set architecture, ISA in short. Unlike high-level languages, we find lots of hardware information from assembly language. Why don't you compare and contrast high-level and low-level programmings? There are numerous high-level programming languages such as C, C++, Java, C#, Ruby, Python, to name a few. Also, there are many ISAs, therefore many low-level programming languages. To name a popular ISAs, we have x86, which is a dominant desktop, laptop, and server processor. ARM, which is in our phones, smartphones, and tablets, and PowerPC that Apple used to use for their Mac before they moved to Intel x86. When compared to high-level programming, the low-level programming is more difficult to program, read, debug, and maintain. Also, it's not very portable to other processors. In contrast, the high-level program is very portable. We simply compile it again to generate a different machine code for different processor.